All right, guys, here we are with chapter 14, problem 62. The figure is a top view of an object of a mass m connected between two stretched rubber bands of length L. The object rests on a frictionless surface. So we're looking top down on this, and this block is allowed to slide back and forth on a frictionless surface. At equilibrium, the tension in each rubber band is T. Find an expression for the frequency of oscillations perpendicular to the rubber bands, so up and down in this picture, and assume the amplitude is sufficiently small that the magnitude of the tension in the rubber bands is essentially unchanged as the mass oscillates. All right, so we need to draw a sketch when the mass is displaced from the equilibrium position. Angle theta here, angle theta here. Now, if our angle theta is sufficiently small, the stretched length of this rubber band will be roughly the same as the unstretched length. So this hint here that assume the amplitude is sufficiently small, that's a hint that we're just going to be looking at small oscillations. So we're going to go ahead and call this length of the stretched rubber band L2. And if this distance delta y here is sufficiently small, this is a totally reasonable approximation to make. All right, so this is what the stretch setup looks like. Let's go ahead and do our free body diagram. We have a tension force that points this way, and a tension force that points this way. Angle theta, and gravity points into the page here because this is on a tabletop. So we're interested in oscillations in the y direction, and our x forces, I think by inspection we can see, are going to cancel. So let's do the sum of the forces in the y direction. That's going to be two of these tension forces. They're perpendicular components, which is times the sine of theta. That's the sum of the forces, and that's going to be equal to the mass times the acceleration in the y direction. All right, so we've done our free body diagram, we've summed the forces. Now we need to figure out what the period of oscillation is going to be here. And so what I propose is that we massage this into the regular format that we see for the equation of motion, which means we have the acceleration set equal to something. So we're going to solve this for the acceleration. We get the acceleration in the y direction is equal to 2t divided by the mass times the sine of theta. Okay, now if this distance is L here, the sine of theta is the opposite, which is this delta y, divided by L, and delta y is down, or in the negative y direction on here. So we're going to replace sine theta is approximately equal to delta L over L. I say approximately because this L is actually stretched a little bit, but since we have a small angle, we're going to assume that the stretched length is roughly the same as the original length. You can get at this small angle approximation in a couple of different ways, but I think that that is conceptually all there. So let's go ahead and plug that in for theta. Excuse me, this is delta L. This should actually be minus delta y, because we go down a distance delta y. So we can plug that in for sine theta. We get the acceleration in the y direction is equal to minus 2t over m over L, all times delta y. Now you may recall for the regular Hooke's law expression, this is an aside here, that we had the acceleration in the y direction was equal to minus k over m times delta x, or delta y, I guess if I'm saying the acceleration in the y direction. And when we solve this differential equation, we discovered that this coefficient that multiplies delta y is in fact omega squared. So in the same spirit, this coefficient that multiplies delta y here is omega squared. So we have omega squared is equal to 2 times the tension divided by m over L, divided by m times L, or omega is equal to the square root of 2t divided by m times L, or the frequency is equal to omega divided by 2 pi, which is equal to 1 over 2 pi times the square root of 2t over m